Darkness still covered much of the South Pacific when instruments thousands of miles apart registered the same unmistakable signal. Seismic waves radiated outward through the Earth, racing across continents and oceans before reaching monitoring stations around the globe. Within minutes, computers identified the source. A magnitude 6.3 earthquake had struck south of the Kermadec Islands at approximately 33.806 degrees south latitude and 179.473 degrees east longitude. Its focus was exceptionally deep, occurring approximately 140.5 miles or 226.1 kilometers below the ocean's surface. At first glance, the event seemed modest compared with the giant earthquakes that occasionally dominate international headlines. There was no devastating tsunami warning spreading across the Pacific. No dramatic footage of collapsing buildings filled television broadcasts. No major population centers lay directly above the rupture zone. Yet among geologists and seismologists, earthquakes like this command immediate attention because they occur within one of Earth's most extraordinary geological laboratories. Every tremor inside the Kermadec subduction system offers another glimpse into the immense machinery constantly reshaping the planet from below. Stretching northward from New Zealand toward Tonga, the Kermadec Trench forms one of the longest and fastest converging plate boundaries on Earth. Here, the Pacific Plate relentlessly dives beneath the Australian Plate, descending into the mantle at remarkable speeds approaching nearly 3 inches, or roughly 8 centimeters, every year in its northern sectors. While such motion appears insignificant over the course of a single day, the effect becomes astonishing when measured across centuries and millions of years. Entire sections of oceanic crust disappear into the Earth's interior, where unimaginable temperatures and pressures slowly recycle them into the mantle. The earthquake recorded during the early hours of coordinated universal time occurred not along the shallow interface where many of the world's destructive megathrust earthquakes originate, but far deeper inside the descending slab itself. That distinction changes everything. Instead of representing the sudden release of stress between two massive tectonic plates sliding past one another, this earthquake appears to have occurred within the Pacific Plate after it had already plunged hundreds of kilometers into the Earth's interior. By the time the rupture happened, the ancient ocean floor had traveled far beyond sunlight, beyond seawater, and beyond the sediment layers resting atop it. It had entered an environment where pressure reaches several gigapascals and temperatures continue climbing with increasing depth. Although hidden forever from direct observation, this underground journey never occurs quietly. As oceanic crust sinks deeper into the mantle, enormous forces begin transforming both its minerals and its mechanical behavior. Rocks that once fractured easily on the seafloor encounter conditions that squeeze every pore and alter their crystal structures. Water trapped inside minerals gradually escapes through chemical reactions, changing the physical properties of surrounding rock. Internal stresses accumulate as the descending slab bends, stretches, compresses, and adjusts to the immense forces acting upon it. Even hundreds of kilometers below the surface, these stresses sometimes become too great. When that threshold is crossed, the result is an earthquake capable of sending seismic waves throughout the planet. According to the published moment tensor solution, the earthquake exhibited a very strong double-couple component, accounting for approximately 90% of the total seismic signal. That characteristic strongly indicates conventional fault motion rather than an explosion, volcanic source, or other unusual seismic process. The calculated seismic moment measured approximately 3.642 multiplied by 10 to the 18th Newton meters, corresponding to a moment magnitude of approximately 6.31. For scientists, numbers like these are far more than technical details. They serve as fingerprints left behind by the rupture itself. The earthquake's focal mechanism reveals the orientation of the fault plane, the direction of slip, and the forces acting before failure occurred. Two mathematically possible fault planes emerge from every moment tensor solution, leaving experts to compare those possibilities with the surrounding tectonic setting before identifying the most likely rupture surface. In this event, One nodal plane shows a strike of approximately 216 degrees, dipping 28 degrees with a rake near 104 degrees. The alternate plane strikes approximately 20 degrees, dips 63 degrees, and carries a rake of approximately 83 degrees. Both solutions indicate movement dominated by compressional forces with a substantial reverse fault component. That finding aligns remarkably well with the broader tectonic environment surrounding the Kermadec subduction zone. The Pacific plate is continuously forced downward beneath the Australian plate, placing enormous compressional stress upon sections of the descending slab. Although deep earthquakes remain among the least understood seismic phenomena, reverse faulting within these environments often reflects internal deformation as the slab continues adjusting during its descent into the mantle. One remarkable aspect of this earthquake lies not only in its depth, but also in its location within an exceptionally active seismic corridor. The Kermadec Tonga subduction system consistently ranks among the most productive earthquake-generating regions anywhere on Earth. Historical earthquake catalogs reveal thousands upon thousands of recorded events scattered along this immense plate boundary. Large circles marking powerful earthquakes cluster densely along the trench, illustrating more than a century of accumulated seismic activity. Several earthquakes exceeding magnitude 8 have struck different sections of this plate boundary during the modern instrumental era. The 1917 magnitude 8.2 earthquake, the 1976 magnitude 8.0 event, and the 2006 magnitude 8.0 Tonga earthquake each demonstrated the tremendous energy capable of accumulating where these massive tectonic plates interact. Yet the latest earthquake occurred far deeper than the typical megathrust events responsible for generating destructive tsunamis. Its hypocenter places it within the descending Pacific slab itself, rather than near the plate interface close to the ocean floor. That distinction significantly reduces the likelihood of substantial vertical displacement of the seafloor, explaining why deep earthquakes of this type rarely generate major tsunami waves despite their considerable magnitudes. The ocean floor above the rupture remained largely unchanged. Far below, however, the ancient crust experienced another chapter in a journey that has continued uninterrupted for millions of years. Every segment of oceanic lithosphere begins life along spreading centers where molten rock cools to create new seafloor. Over tens of millions of years, that crust gradually drifts away from the ridge, cools, thickens, and becomes denser. Eventually, gravity itself contributes to its descent back into the mantle once it reaches a convergent plate boundary like the Kermadec Trench. This continuous recycling process represents one of Earth's defining geological engines. Without plate tectonics, continents would never have assembled and separated repeatedly throughout geological history. Mountains would not rise in the same way. Volcanoes would behave very differently. Even the long-term cycling of carbon between Earth's interior, oceans, atmosphere, and crust would fundamentally change. The magnitude 6.3 earthquake serves as another reminder that this enormous planetary engine never truly rests. The location of the rupture also highlights why the Southwest Pacific attracts such intense scientific interest. Unlike many subduction zones where convergence proceeds relatively slowly, portions of the Kermadec Tonga system move among the fastest anywhere on Earth. Plate convergence exceeding approximately 3 inches, or about 8 centimeters, each year continuously injects fresh stress into the boundary, while carrying oceanic crust steadily downward into increasingly hostile conditions. That rapid motion contributes to an extraordinarily complex pattern of earthquakes, spanning from the shallow ocean floor to depths exceeding 435 miles, or approximately 700 kilometers. Few places on Earth display such an extensive vertical range of seismicity. Scientists map these earthquakes carefully because together they reveal the shape of the descending slab hidden deep beneath the Pacific. Each earthquake effectively illuminates another tiny portion of an otherwise invisible structure extending hundreds of miles into the mantle. Over decades of observations, these countless seismic events combine to create one of the clearest images available of a tectonic plate disappearing into the Earth's interior. The latest rupture now becomes another precisely located point within that growing three-dimensional picture. While residents across much of the Pacific may never have noticed the shaking from such a deep event, sensitive instruments certainly did. Modern global seismic networks detect vibrations traveling through the entire planet, allowing experts to reconstruct the earthquake with extraordinary precision. Arrival times of primary waves, secondary waves, and later seismic phases provide independent constraints on the earthquake's depth, location, and source characteristics, transforming a few seconds of fault movement into a remarkably detailed scientific portrait. Far beneath the South Pacific, the earthquake had already ended before most people around the world even learned that it had occurred. The rupture itself lasted only a matter of seconds. The geological forces responsible for it, however, have been building for millions of years and will continue operating long after every witness alive today is gone. One of the most fascinating aspects of this magnitude 6.3 earthquake is that it occurred at a depth where ordinary rock should no longer behave the way people imagine. Near the Earth's surface, brittle rocks fracture much like glass or concrete when stressed beyond their limits. At depths approaching 140 miles, or approximately 226 kilometers, temperatures and pressures become so extreme that many rocks are expected to deform gradually instead of snapping apart. Yet deep earthquakes continue to challenge that expectation. Scientists have spent decades trying to explain why earthquakes remain possible hundreds of kilometers beneath the surface. Several competing mechanisms have emerged through years of laboratory experiments, seismic observations, and computer modeling. Rather than one single explanation fitting every event, different processes may dominate at different depths and in different sections of a descending tectonic plate. One leading idea centers on the remarkable journey of water. Although the Pacific plate appears dry on the ocean floor, it actually carries significant amounts of water locked inside minerals that formed during millions of years of interaction with seawater. Tiny fractures within the crust become filled with seawater long before the plate reaches the trench. Chemical reactions transform portions of the oceanic crust and upper mantle into hydrated minerals capable of storing water deep within their crystal structures. Once subduction begins, that hidden water accompanies the plate downward. As temperatures steadily increase with depth, many of those minerals become unstable. They begin releasing the water trapped inside them through a sequence of metamorphic reactions. The escaping fluids may temporarily weaken surrounding rock, reducing friction along existing fractures or creating conditions favorable for sudden rupture. This process, often referred to as dehydration embrittlement, remains one of the strongest explanations for many intermediate-depth earthquakes throughout the world's subduction zones. Another possibility involves mineral phase transformations. At tremendous pressures, familiar minerals become unstable and rearrange themselves into denser crystal structures. One of the best-known examples involves olivine, the dominant mineral within Earth's upper mantle. Under sufficient pressure, olivine transforms into entirely different mineral structures while occupying less volume. These transformations release stored strain energy and may trigger localized faulting inside the descending slab. Whether dehydration reactions, mineral transformations, thermal stresses, or a combination of several mechanisms dominated this particular earthquake remains an active scientific question. What makes the event valuable is that every accurately recorded deep earthquake provides another opportunity to test these competing theories against real observations. The moment tensor solution offers additional clues. Its dominant reverse faulting character reflects compression within the slab rather than extension. That observation is consistent with sections of the Pacific plate continuing to adjust as they descend into the mantle. Far from behaving as a perfectly rigid sheet, the plate bends, twists, compresses, and flexes throughout its journey. Every change in geometry redistributes stress, and eventually, certain sections exceed the strength of the surrounding rock. The resulting rupture sends seismic energy racing outward in every direction. Unlike shallow earthquakes, deep earthquakes often transmit their seismic waves remarkably efficiently. Because they originate within colder, stronger portions of the descending slab, relatively little energy is absorbed before the waves begin traveling through Earth's interior. In some cases, people located hundreds or even thousands of miles away may feel a deep earthquake that causes almost no noticeable shaking directly above its source. The unusual behavior has fascinated seismologists for generations and serves as another reminder that earthquake magnitude alone does not determine how shaking will be experienced. Fortunately, this event occurred far from major population centers. Its great depth also significantly reduced the likelihood of severe surface damage near the epicenter. As seismic waves traveled upward through more than 140 miles, or approximately 226 kilometers, of rock, much of the highest frequency energy diminished before reaching the surface. The result was an earthquake of scientific importance, rather than one remembered primarily for destruction. That distinction matters. Powerful earthquakes occurring within remote sections of the Pacific frequently become invaluable natural experiments precisely because they unfold without producing widespread humanitarian disasters. Scientists can focus entirely on understanding the physics of the rupture, refining seismic models, and improving knowledge of Earth's interior without simultaneously responding to catastrophic damage. The Kermadec Trench itself remains one of the least familiar yet most important geological features on the planet. Stretching for roughly 900 miles, or about 1,500 kilometers, it forms an immense scar across the southwest Pacific, where the Pacific Plate begins its descent beneath the Australian Plate. Above the trench lies an equally impressive chain of submarine volcanoes and volcanic islands created as water released from the descending slab lowers the melting point of rocks within the overlying mantle. Magma generated by that process eventually rises toward the surface, feeding one of Earth's most active volcanic arcs. Earthquakes and volcanoes therefore share the same fundamental engine. The sinking plate not only generates earthquakes through accumulated stress, but also provides the water necessary to promote melting and volcanic activity. Every deep earthquake occurring beneath the volcanic arc contributes another piece to understanding this intricate relationship between subduction, mantle chemistry, magma generation, and seismic activity. The historical record demonstrates that the Kermadec-Tonga subduction zone has repeatedly produced some of the world's largest earthquakes. While this magnitude 6.3 event released only a fraction of the energy associated with the giant magnitude 8 class earthquakes documented along the plate boundary, it nevertheless forms part of the same ongoing tectonic process. It is essential, however, to avoid drawing incorrect conclusions from individual earthquakes. One earthquake does not necessarily signal that a larger event is imminent. Deep earthquakes like this one occur through different physical mechanisms than the shallow megathrust earthquakes responsible for the greatest tsunami hazards. Although scientists continually monitor seismic activity across the region, there is no scientific basis for interpreting this earthquake alone as evidence that a much larger rupture must immediately follow. Earthquake sequences often appear meaningful simply because humans naturally search for patterns. Modern seismology instead relies upon statistical analysis, historical records, geodetic measurements, and detailed studies of fault mechanics rather than isolated events. Each earthquake contributes valuable information, but no single event can reliably predict the timing of the next major rupture. Even so, the latest earthquake strengthens one undeniable conclusion. The Kermadec subduction system remains extraordinarily active. Its continuous plate convergence ensures that stress is constantly being redistributed throughout the descending slab and along the plate interface. Earthquakes ranging from tiny microseisms to giant megathrust ruptures will almost certainly continue occurring as long as plate tectonics reshapes the Pacific Basin. For scientists, every precisely located earthquake improves tomographic images of Earth's interior. Seismic waves generated by events like this pass through thousands of miles of rock before arriving at monitoring stations worldwide. Tiny differences in travel time reveal subtle variations in temperature, composition, and density deep inside the mantle. Much like a medical computed tomography scan builds an image from many different angles, global seismic observations gradually reveal structures that no drill could ever reach. That is one reason why earthquakes remain among the most valuable scientific tools available. Without them, humanity would know remarkably little about the planet beneath its feet. Every earthquake functions as a naturally generated pulse that illuminates hidden layers extending from the crust to the core. The larger and better recorded the earthquake, the more information scientists can extract about regions forever beyond direct observation. The magnitude 6.3 earthquake south of the Kermadec Islands may never dominate international headlines, yet its importance extends far beyond its immediate location. It represents another measurement within one of Earth's fastest subduction zones, another confirmation that the Pacific Plate continues its relentless descent beneath the Australian Plate, another glimpse into the mysterious behavior of rocks under extraordinary pressure, and another reminder that our planet is constantly evolving, even where no human eye can witness the process. Far above the rupture, the Pacific Ocean appeared calm, with waves continuing their endless rhythm across one of the most isolated stretches of water on Earth. Far below, the ancient ocean floor had shifted once again during its irreversible descent into the mantle, releasing energy accumulated over years, decades, or perhaps even centuries. Instruments scattered across the globe faithfully recorded that fleeting moment, transforming invisible vibrations into data that scientists will analyze for years to come. Long after the seismic waves faded into the background hum of Earth's continuous motion, the tectonic engine beneath the Kermadec Trench continued operating exactly as it has for millions of years. The Pacific Plate is still moving, the Australian Plate is still resisting, stress is still accumulating, minerals are still transforming, water remains locked inside descending rocks before slowly escaping under crushing pressure. Volcanoes continue receiving the ingredients needed for future eruptions, while earthquakes continue tracing the hidden outline of a tectonic plate disappearing into the depths. The latest magnitude 6.3 earthquake is not the end of that process. It is another precisely timed heartbeat within one of the most powerful geological systems on Earth, offering scientists another rare opportunity to understand the immense forces that continually reshape the planet from the ocean floor to the deepest reaches of the mantle.